Hello, good morning everyone. So today I would like to start the lecture 9. So in this lecture 9, before we going into the detail for the lecture 9, I would like to review a little bit to the lecture at what have we learned. It's only to the relevant point. So we will, oh, okay, sorry. Of lecture 8. Maybe I change the color a little bit. So a little bit reviewing. What did we learn last time? We learned about the dynamic. It's really important. I hope you still remember what is the dynamic. So the dynamic is just the object have the movement is not in the equilibrium state. Means we apply the force is moved, and in this dynamic we learned two words last time. Kinematics. What is kinematics here? Kinematic is about the movement of the objects. For example, the velocity, the displacement and accelerations. Without any relation, what does it come from? For example, the ball is moving in this side by this velocity. For example, 10 meters per second. For example, it moves. This is the starting velocity, and then you ask the 10 meters. And then if acceleration is 0, then when does this ball arrive to this final positions? For example, but this not related to force, to mass or anything. So this is what we learned last time. We already finished this, and this time in this lecture we will learn about kinetics. Okay, so this is what we will learn about in this lecture 9. So let's see what is kinetic is in a few slides. Okay, so let's start. So the chapter today is about the kinetic of particles, and this is really correlated to the Newton's second laws. So what about the particles? I think you still remember the particle is the simplified point from the whole mass. For example, if we have a car like this, instead of having those car, we transform it to only particle to the point. For example, this point have this mass mg and has a force, for example, but instead of writing those whole object, we simplify it to only single point particles. Okay, next, kinetic of particles. By the way, what is kinetics here? If you go back to last lecture, the definition of the kinetic is what? It is about the relationship of the movement of the objects and also the force and also with the mass. So we have objects like this, and then this is movement, and then we will find the relationship between movement to the mass and force. So these three will be in our equations, okay? And you will see in the next few slides. Okay, so let's see what is this thing here in our slide. So let me remove this. Okay, so that we can have full screen. So we have a man here. So if we write him as a particle, and then the movement is in this way. So we have an acceleration in this directions. And then we have to analyze all the force on the wheelchair in order to design a good ramp. Because of course, you have also the angles, because you have this ramp, the angle. Then you have also the angle of, for example, 20 degree angles. And then how much force you needed. Oops, sorry. How much force you needed to moving up from this ramp, for example. This also correlated to mass of this guy on a wheelchair, and how much he put the force by his hand to the wheels so that he can move up to the ramp. Okay, next one, next picture. What is this about? High swing velocity can result in the large force swinging from the chain or rope, causing it to break. Okay, so to move, when you have very high velocity or accelerations in this swing, so it's just like pendulums. So you have an object, you swing like this, okay, and then you also introduce the tensions, or you can call it force in this rope. So if you swing it too much and you have too much weight, where is mg from this girl, and you have too much force by the weight from this girl, so you might also cause more tensions. The tension is too much, so that this wire, this chain also could break. So this breaking, according to what? Accelerations, mass, and also the force. Alright, so maybe you now getting the picture of what is kinetics. You know, last time we only studied for kinematics. Okay, this is kinematics. Please be careful. We have another kinematics. Kinematics, last time we studied about, we have a ball, we shootings, and then when it hit the ground, when does it hit the ground, or how long would the ball travel? So we only study about when it hit the ground, or how long x is traveling. We didn't involve any force or mass, so we didn't involve any of this. Oops, my bad. How can I get? So I'm a little bit struggling now. Okay, I just try to change the color of the pen, but no. Keep. Alright, so I just try to have the color of the pen change. Okay, so we don't have any mass or force in this case, in kinematic case, okay? But as you can see here, in this kinetic stuff, we have mass, we have movement, and we have force. We have this three all in there. Okay, so this is the difference between kinematic and kinetics. right? Next, let's see. Put full screen again, even I'm afraid that I cannot put it back. Okay, so I go with green. Introductions. So now you would like to have the relationship of the force, movement, and the mass. And here is the governing equations for the questions. Okay. So let's begin. You remember the Newton laws, second laws? We have F equal to ma. So now we have an object, and the object is moved by some force. So for example, you're just dragging you're dragging the box. So you are like this. We have the box, we have a rope, and you dragging the box forward. So we have a tension force applying to the box, and the box moving by your force. But then you also have some frictions from the ground to the box, and we will take a look at it together later. Okay, right? So next, the Newton's second law of motions. If the resultant force acting on the particle is non-zero, which means we have some movement, the particle we have acceleration proportional to the magnitude of resultant force and in the direction of the resultant force. Okay, next, it also must be expressed with the respect to Newtonian or initial frame of reference in one that is not accelerating or rotating. Okay, so in the question you will see that we will have also the reference, also we will have a frame and coordinates also, and you will learn later that we have also and the frame itself will not rotating or have any accelerations, right? For example, your frames is setting here X and Y, and this frame must not accelerating or rotating while you are solving this problem. Otherwise, this Newton law is not effective anymore. It cannot calculating the correct acceleration and force that you apply to the problem. So this form of equation is also have a mass constant here, every time constant. Okay. Okay. So next, linear moment of particles. So this one you learn about this word a lot. Linear momentum of particles. This linear momentum L is nothing but mv. Okay. If you have a velocity of the mass in one directions, it say that if you have no force, mean you have constant linear momentum of particles. Okay, so if there is no force, means the velocity at that point will become constant. So okay, so you can also read it through this sentence. If the resultant force of the particles is zero, the linear momentum of the particle remain constant. in both magnitude and directions. So okay, and you can see that this F equal to ma when you have force as 0. It also means if we have a constant m, because you need to have some mass, means acceleration is 0. What does it mean by acceleration 0? When you're driving the car with the car again my bad drawing for the car, moving of velocity of 100 hours. What a stupid of mine. 100 kilometer per hour. Okay, but then you say acceleration is 0, means you have 100 kilometer per hour constant all the time. It doesn't mean you didn't have any velocity, but your velocity becomes freeze and constant. Okay, next, unit systems, because in this case you encounter a lot of the force and also pound here and slugs, means you need also to transform these two forces. Okay, so here for 1 newtons we have kilogram and meter per second square. So newtons actually is equal to kilometers per second square, and here is for the US units. Okay, so you have to know what this is about of this units. Means when I have, for example, mass of 100 grams, you cannot put this mass into the formula of F equal to ma. Why? Because if you put it directly, you will got grams multiplied by meters per second square, and when you transform this to newtons, this is wrong. So before you putting in this mass, you have to transform it to kilogram first, which is 1.1 kilograms, and then you have to put this into the formula, then this is valid, so this one will become kilogram. Okay, so every time before you solving the problem, please change all the unit into the SI units, means gram to kilograms, millimeters to meters, or if we have a minutes or we have hours, you have to change it to seconds. Okay, next, equation of motions. So from last couple of the chapters, you still remember we learned about first Newton law, F equal to 0, sigma F equal to 0, sigma m equal to 0 for the statics. Okay, and then we have Fx equal to 0, we have sigma Fy equal to 0, and we have sigma m at some point equal to 0. Here is the same for, say, for this problem we will also have the same. This is static. Okay, for dynamic we have the same. We have the force in 3 coordinates also. No, not coordinates, but we have the force in 3 axes in the coordinates. So as I told you before, we have to creating the frame, we have to creating the coordinates, and this coordinate we often use is, what do we call this? Cartesian coordinate. Okay, and we have another one. What does it call? Polar coordinate. I hope you still not forget about this. And this we have x, we have y, we have we have c, and then you can see that in the second Newton laws, we can use the scalar component equations. For example, for the rectangular components here, so you can also have something like this. Because our force is in the coordinate of 3 axis here, so we have force of x, force of y, we have force of z, and then we have acceleration in x, in y, in z, and then out of this you can also decompose this into different equations here. Okay, so you encounter a lot of these equations because we will most likely we will have 2D x and y in the questions, in the problem. Okay, so at least we will have sigma f x equal to max, and we have sigma fy equal to may, right? So dynamic equilibriums, can we make the dynamic equilibriums? Because you know already, when we have the objects, we move by force, and the direction of the movement also in the same direction as force. You can also play a little bit tricks. So normally we have sigma f equal to ma. You can move ma to another side, so we have sigma f minus ma, and this equal to 0. So means you have to find the equilibrium of the force and the negative movement of the mass. So you can see here. So here is the equilibrium system, but of course you have to modify a little bit of equations. So here we call inertial vector. Okay, with the inclusion of the inertial vectors, the system of force acting on the particle is equivalent to 0. The particle is in the dynamic equilibrium. So this we call dynamic equilibrium. Please be careful. We can use the word equilibrium also in dynamics, but we have to modify a little bit the equations and the understanding. Okay, so this is also not really also we can also have it in polar coordinates, and here you can see we have t, we have in plane, we have the in plane of the axis, we have the tangential axis, and then you can also using the equilibrium of this equation, so we will have something like this. So means we have sigma f minus ma equal to 0, but you know this one we will have a of tangential plus a of normal plane. Okay, so this is really important. We have to draw the free body diagram again, and also kinetic diagrams. What is a free body diagram? What is a kinetic diagram? Let's see. So first, if you have a pump, you have to isolating the body of the interest. For example, if you are interested in this box B or box A, if you're interested in box A, you eliminating box B and replace it with the force that interact between the box A and B. Okay, but in this case we interested in box B, so we will only isolating box B here. So we have a B box, and then next we draw the axis of the system. Okay, so you can also write this axis, but since this box is a little bit tilting, so it's better to writing in the same directions or same angle as a box, but also depends on you. If you didn't do this, then you also have to use the sine and cosine law to also the projecting the vector into your coordinate system. But in this case, you have, for example, this force and also velocity in the same axis as your coordinates, so you not need to do the sine and cosine on the acceleration and force, but maybe you have to do it on mass, of course. And then you apply the force like this, as I did before. So we have a force and we have a mass mg, and next also replacing the support with the force. So you add the applied force, so and also you replace it with the support from the force here. So you know that you are interacting with the another objects also, right? So that's why you have a normal force. Normal force means if you have an object in any angles, you have a perpendicular to the plane that you are in contact with another object. We call it normal force. So you can see here is a perpendicular to this contact plane. And then next we draw the appropriate dimension, usually angle for particles. Of course, we have this angle. We also have to project it here, so that we know when we use cosine law, we will have to change the direction of the vector. For example, we have to change the direction of the vector of mg. Okay? So, now, this is what we call free body diagrams. But here is kinetic diagram. What is the kinetic? Oh, this is a bad move for me. So I need to erase this, but how? Okay. Good. Okay, so we have this. So first isolate the body of interest again, similar to FBD here. And then draw in the mass time accelerations of the particles. If unknown, do put the positive directions according to your chosen axis. Okay, so now this is what we have to do in the kinetics problem. We will have force, we will have a mass, so we will have two diagrams that we have to draw. Okay, you have to draw the free body diagram on the left side, and you have to do the kinetic diagram on the right side. And then this diagram represent MA, and these diagrams represent all the force in the system. Next, then let's try draw the free body diagram and also kinetic diagram for the block A. Note that this is massless, so there is no mass, no mass, and frictionless. Oh, no. I didn't read it through, but they say this is of this, no mass, and frictionless. Okay. Let's see, we do it for block A here. So first thing we have to do, isolate the bodies. So we have only this body without the axis here. Next we apply the force. So how many force do we have here? We have a lot. And also we have a replace support with the force. So you can see now there's a lot of force by the supports, okay? Because here, okay, so you have also here we have the force actually by what? By the friction between the object A, or no, object B to this object A. And then also we have normal force. So here is a friction force and normal force. Every time you have to do it when you are in contact with another object. Remember, you have two things you have to draw. First, normal force. Second, friction force. Okay. Next, also we have these two from the ground. Remember, we have these two contact, this block bay also in contact with the ground, and T here. So this T also in contact, getting pulled by the cables also, and also this part also a part of the block A, because you know this is tied together, this is tied together, so this is a part of block A. And we also have a tension there. So, but you can see clearly that these two, if we make a plane like this, if we make a plane like what we did, these two will cancel each other. Okay. So next, dimensions. Alright, dimension here we already drawn. So here's our dimensions. And kinetic diagrams. So we have no movement on the y-axis. How do we know? If you have a movement on y-axis here, that means your box is jumping up, which is not in this case. Your box will rest on this ground all the time. So there's no movement of the box in the y-axis, so you can say it's 0. And on the x-axis, this now become interesting. So now we have a movement in the x-axis here, right? Okay, so next, free body diagrams and the kinetic diagrams. Can you draw for this color B? Assume that there is a friction between the rod and the collar. So here is collar, here is rod A, collar B. The motion in vertical plane and the angle. So we have the motion in this and this plane. Here we isolate, and then next we written the axis, and we apply the force, we doing the support, we have the dimensions, and we draw the kinetic diagrams. That's it. So this force is the force in plane in our axis, and then you also have mg, mass of this objects also have to be written all the time. And also we have the reaction force N, okay? Because you know this object is in contact with the rod is like this, so you have also the normal force. Okay, so let's get into our sample here. Okay, let's see, we have sample pump 2.1. We have block rest on the horizontal plane. Find the magnitude of the force P required to give the box as an acceleration of feet per second square to the right, and the coefficient of kinetics friction between the blocks and the plane is mu k equal to 0.25. Does anyone know about the friction force? So I will write a little bit. Oh, by the way, it will be taught on this question. So, yeah, let's go through this question together so that we learn about the friction force. Right. So, okay. Let's see. So here's the solutions that you're going to do. Follow this step. So first, solve the equation of the motion block into rectangular component equations. Of course, we have sigma f equal to ma in x and y axis. So what you have to do first actually is, okay. So what do we have here? So we have an object. Let's see what is the color of my pen right now. I would like to have sample 12.1. We have objects. So first we draw free body diagram. Okay, we have objects, we have force. Here, what do we have here? We have a weight. We have a weight of 200 pounds. And then we have also, next we draw also the coordinates. So we have the coordinates x and y. Don't forget about this. Okay. And then we draw the force. We have force P. Okay. And then we have draw the support. Next we draw the support force, reaction force. So we are in contact with the ground, so we have Newton, we have normal force, and also we have friction force. First law, frictions always in the opposite directions of the force you apply it to, because this friction force will resist the force that you apply it to. For example, you apply force P in these directions to the right, then the friction force will be to the left, right? And last thing you have to do, you put the dimension in. Okay, 30 degree there. And okay, so we have pretty much everything. Then we have to draw kinetic diagrams. We have this, and then we don't have any movement in the y-axis, so we have only movement in the x-axis here, ma. Okay, and first we have a wedge, but in the equations F equal to ma, do we have a wedge there? We have to change the wedge to the mass. So what is the formula for that? So mass equal to wedge over gravitational force, and then we have 200 pounds over 32.2 feet per second square, and then we will have 6.21 pound per second square feet. Okay, so next, next, so now you already have what you know, and another one, friction force. So I would like to define this first. Friction force, we have mu k equal to n. Okay, remember this, and please understand that this friction force, if you have an object and you have friction force, it will become larger if you have more normal force here. So friction force equal to the friction coefficients multiplied to the normal force. For example, if you moving the box and the box has a lot of weight, means you have a lot of normal force, then it's harder to move the box. Okay, so this is the logic behind. So I erase this. Right, then first resolve the two force component equations. So first, you know already we have sigma fx equal to ma x, and we have sigma fy equal to ma y, where ay equal to 0. As you know, there is no movement on the y-axis. So first, let's see sigma fx equal to ma x. So what do we have here in the x-axis? So we have this friction force, we have this p, but of course we have to change there, we have to decompose it into the correct axis here. So you have two things, and p is p cos 30 degrees, and we have f frictions in negative, right? Because it's in negative directions, equal to ma. And then what is it given here on the right side? We have p cos 30 minus 0.25, which is our friction coefficient here, multiplied by n. No. Multiplied by n. And the mass we already defined up there, we have 6.21 pound second square per feet. And then we multiply with acceleration, also given here. We have 10 feet per second square. Okay, look good. Looks really good. Okay, so next we solve, we just multiply this, then we have 62.1 feet, cancel by feet, second, cancel by second, then we have 62.1 pound. And then let's solve y-axis. So we have So this will be our p cos 30 minus 0.25, and this will be our equation 1. Okay, and then next we have sigma fy equal to may equal to 0. And then here we have on the y-axis, what do we have there? We have also it's not good to highlight, it's in yellow, but anyway, I will just circle this. We have this one, and we have p in another direction. So we have p sine 30, and the p is in the negative because this is down, and we have plus normal force equal to 0. Then in the end we have n equal to p sine 30. Forget this one, sorry. So we also have this wedge, 200 pound wedge here. So let me erase this. Minus 200 pound equal to 0. So in the end we have n equal to p sine 30 plus 200 pound, and then you can just put this 2 into 1. So you substitute n by these equations. So you will have p cos 30 minus 0.25, n is p sine 30 degree plus 200 pound equal to 62.1 pound. And then when you solve this, you get p equal to 151 pound. Okay, so that's it for the first questions. And next, a little bit more complicated of this. Let's see. So we have two blocks, and show from the start, rest on the horizontal plane, and the pulley are frictionless. Again, the pulley is frictionless. And massless or no mass. Determine the accelerations and of each block and the tension in the cord or cable, you can say. Alright, so okay, let's try this sample. Oh, is this really restricted? Okay. Okay, so let's write our own pictures. First, we have y. We have 1 kilograms mass, and we have this pulley. Okay, and this pulley has also the mass B, mass A, and this is 300 kilograms. Okay, so what do we do first? We draw the free body diagrams, right? So F, no, Y is moved automatically back. So we write FBD here. Okay, and we focus on A first, object A. So I will just write this as object A. We have wedge A. We have tension in this direction, right? First we draw the force. Secondly, we draw the coordinates. We have the coordinates. I would suggest do it like this: y and x. This is all. Okay. Then we have next also drawing the support force, reaction force. We have newtons. No, we have normal force here. And then we draw, of course, the angle or the dimension, but in this case we don't have it. Next, we draw the kinetic diagrams. We have objects, and we know is this MA, AA. Okay, so and our MA is equal to 100 kilograms. Next, I will draw it for this. I would say I will do it in yellow. 300. Okay, so here also we have tension. We have tension T1. We have tension T1, T1. And here we have T2. Okay. The first. Okay, then now we start with B. We have block B. We have tension T2. Okay. And then we have also the mass, the wedge of the WB, but then we are not calculated yet. WB is equal to mg, and then we have to draw the kinetic diagram. We have MB, AB, okay. And MB is equal to 200 kilograms. Right. Then okay, then now we draw the diagram that we needed, and let's go for the solving. So what we have, what we would like to know is we would like to know the tensions, and we also would like to know the accelerations. Okay, so in this case they ask for acceleration A is equal to what, and acceleration B is equal to what, and tension A, or we are not calling tension A, but we have tension 1 is equal to 1 and tangent 2 is equal to what? And okay, let's start. So if you remember in the last chapters, there is a relation between the rope and the pulley. So you have to know that when we have this kind of pulley, remember that when we move this y, and the movement of this will be y over 2. Same case here. So we have the movement of yb is equal to half of the movement of xa. So to say this one, we say AB, acceleration of AB is also half of acceleration of A. So this is our first equation. Next, you also know that our tangent there from the pulley T1 and T2, what is the relation from T1 and T2? So T2 is equal to 2T1. Okay, so this is our also equations. And next, we would like to solve the problem. So we have sigma f x equal to ma AA. So in this case, for the object A, you only have the movement in the x. Okay, and there is no friction force. There is no frictionless. Is there also? Because there is no friction coefficient given. Also, so fx is equal to what? We have only, I will highlight it in white. We have only this. Means we have T1 equal to 100 kilograms time acceleration of A. Right. The next we have sigma Fy equal to MBAB. In this case, we have MBG, because you know, you have a look on this diagram, plus negative T2 equal to MBAB. And when we plug in all the formula in the, all the value in there, we will get 300 kilograms mass, 9.81 meter per second square, minus T2 equal to 300 kilograms AB. So to say T2 is equal to 2,940 newtons minus 300 kilograms AB. Okay, so you have these equations. You have this. No. You have 4 equations, 4 unknowns here. Your unknown is T1 and T2, and AB and AA. Acceleration in A and acceleration in B. So you have 4 equations, you have 4 variables. What does it mean? You can solve it, of course. So how to solve this? Then I will show you by step. First things maybe you have to do is, what you can do, there's 2 solutions. I'm not sure whether your calculator is capable of doing the 4 variable solving equation or not. but here is solving by hand. Okay, first what we can do is we have T2, we have equation 1, we change the say okay we put the equation 1 into equation 4. 1 into 4, then we have T2 equal to 2940 minus 300, AB equal to 1 over 2 A, right? And then next also you can put these equations 4 and 3 into 2, so means you substitute you have T2 minus 2T1 equals to 0, right? Then you using equation 4 to substitute T2 and equation 3 to put in T1, and then you will get 2940 minus 150 AA negative 2 100 AA equal to 0. Then you get AA, solving those you get 8.4 meter per second square. This is the answers, first one. Then you use this one, plug into the first equations. So AB is equal to half of AA, so means AB is only 4.20 meter per second square. And then T1, you can plug in also T1 in the equation 3. You also substitute AA by 8.100 times 8.4 means you will get for 840 newtons as an answer. And for T2 is now equal to 2T1 is equal to 1680 newtons. So here is the answer. Alright, let's have a short break and then we will continue in the next sample.